Okay. Oh, you see? Hello. Okay. Let's get started. And any question from this time? This time we will go in pretty carefully through this concept of 3D composition. And once again, this is a way to characterize entangle's pure state. Okay? So the setting is that we have a bipartite system, that is this part A and part B, and part A and part B are entangled, and they are in a pure state, and they want to see how this part A and part B are entangled to each other. And we find out that, although we didn't exactly quantify entanglement, we find out that we can write this pure state in a way that kind of express how these states are entangled. That is, we can write psi in this streaming decomposition, that is summation over just one I, lambda I, and IA and IB. And IA is basically a basis for system A, and IB is a basis for system B. So it's like a summation over different weights, and those lambda I are non-negative real number with their square sum to 1. Okay. So it's like a summation of 0, 0, 1, 1, 2, 2, etc. Okay. And so, yeah. And we see that if we write the pure state in the streaming decomposition, then it's easy to see the reduced density matrix on part A and part B. So both part A and part B will have a reduced density matrix, this summation I lambda I square and quadrature on I. Okay? And yeah, and in particular, so you see the eigenvalues of the reduced matrices of A and B are the same. And also, if you pick the basis as I and IB, then the reduced matrices between A and B are totally same. Okay. And we have some example of streaming decomposition here. So maybe this 0, 0 plus 1, 1 is a streaming decomposition. And also this plus 1 over square root of plus plus and plus minus minus is a streaming decomposition. And also this plus plus state is a streaming decomposition. But you find out that if we write it in a computational basis, this is not a streaming decomposition. Then it's not obvious that whether this state is entangled. But if you write it in streaming decomposition, you will turn it into the plus plus state. Then you see that this is a plus state, this is a plus state, so this state is not entangled. Okay? And yeah, so although we don't have an exact quantify of qualitative description of entanglement, we see that if you want a state to be totally not entangled, then its streaming coefficient should be 1, 0, 0, 0, 0. Okay? And yeah, and every state has a streaming decomposition. So that's that. Any question? If not, then let's go to the last concept correspond related to the reduced density matrix. That is this idea of purification. And the idea is that we get a density matrix on some system A, and we want to say the idea is really the starting of the idea is this. So it's like a reversal of partial trace. So you think that kind of in our streaming coefficient example. Oh, excuse me. I don't actually have a pen. Okay. Then I guess I need to. Excuse me. I need to draw with my mouse. Okay. Yeah. So in our streaming decomposition example, we have the system A and the system B. Okay. And system A and system B, and we say that they share a pure entangled state, and you trace out one part, then you will get a reduced matrix on B part. You trace out the B part, you will get a reduced density matrix on A part. And purification is kind of a reverse of this thing. It says that we start with some rho A on system A, and is there a pure state on AB, or actually AR, because R for reference, you just change the name. Okay, so and so we have some reduced density matrix on system A. Then is there a pure state such that if you trace all the other part, you become this reduced density matrix on system A. Okay. And one thing to emphasize is that this is only a mathematical procedure. Okay. This is just saying that if we know this row A mathematically, so maybe store in your computer, can you compute some pure state, this AR, such that row A equal to trace AR. Okay? And so this pure state here, is also something we only compute in our computer. So what we mean is that as compared to a physical process, you might think that you actually have a system A in a state row A. Then can you do something to make it this pure state AR? And in general, the answer is no, because if you use this unknown mixed state row A here, then it's impossible to get a pure state AR. Okay. But mathematically, so what we will prove very soon is that mathematically, if you have a state row A here, a density matrix row A here, then you can always find a mathematical state AR such that they satisfy this equation. Row A equal to trace R, AR. Okay. And it's useful for simplifying proofs and get some ideas and get some intuitions. For example, this also justifies our discussion on streaming decomposition. Remember, maybe do this. Okay. Remember when we say streaming decomposition, we say this A and B system need to be a pure state. Okay? And you might ask a lot of state are mixed state, and why can we assume we're a pure state here? And the answer here will be because there is purification. So you can always think so you have a mixed state, and you can always think that your system is a larger system, and in a larger system you are in a pure state. Okay? So purification is very useful in this kind of theoretical thing that is, I guess we just see the use. So basically, it's very useful to say that you can always think about pure state because there exists a purification. So you can just think. Yeah, so when you are doing theory on something and you might get a mixed state, but then you can just say we consider a bigger system, then we only need to deal with pure state. And pure state are just easier to manipulate because it's a vector instead of matrix, so there are just less numbers to keep track of. Okay, so that's purification. And then the theorem that we kind of assume that is true is that every density matrix row can be purified. So whatever system A and whatever density matrix row A, you can always find the AR such that trace AR equal to row A. Okay, so this is a theorem, and the proof is pretty straightforward. And we use one of our favorite tools in this course, that is this diagonalization, okay, or also normal decomposition. Okay, and so we know row A as a density matrix is positive, so it can be unitary diagonalized, and so we diagonalize it and write it in this expression. Row A equal to summation I square root pi, so those are the eigenvalues, and IA. Okay. And oh, sorry, I think I made a typo here, so this should be pi here. Okay, we know it's a density matrix, so this should be those eigenvalues should be between 0 and 1 and the summation to 1, and the eigenvalues can be viewed as probability. So this should be pi here, no square root, sorry. And yeah, so we want to purify row A, and we want to find the system R such that it has the same dimension as A, and it has some orthogonal basis IR. Okay, and then purification, we just have the exact construction here. We say there's AR here. So from this PI here, then PI and those. So from those eigenvalue PI and those eigenvector IA, then we can just write the AR. Just define our AR as summation over I. Then now we take a square root P square root. So PI becomes square root PI, and this IA tensor IR state. So it's an entangled state, and you see that this is already in streaming decomposition, so it's pretty cool. This is a summation only one I, and some lambda I here, and IA IR. Okay. And yeah, so IA is also normal basis because also normal because this is unitarily diagonalizable, and then IR is just whatever also normal basis we choose. Okay, so AR is this, and we think this is just a purification of our state. And so the rest of proof is we just need to do trace R on this thing and prove that and see that it's actually row A. Okay, and yeah, so the rest of proof is to test that our AR actually do what we want to do. Okay, so trace R of AR, and so AR has one summation I. So this first AR is a summation I, and the second AR give you a summation J. So you have summation IJ, and everything is IJ. So square root of PI PJ and IJ and and IRJR. And now we remember that we need to do trace R. And so that's doing trace on the R part of this state. Yeah. And we know trace this partial trace is linear, so all those parts that doesn't depend on R, we can just pull this trace inside to only the R part. Okay. And the trace R, IRJR. And then by the second rule, that's the inner product between IR and the JR. But we know this IR is also no basis, so this is just delta JR, and this is delta IJ, and this delta IJ can cancel with this I to make it to cancel with this summation J to make things just summation I, and so I guess. We can write one more step here. So this thing, you cancel this summation ij with this summation j, then you have the summation I and pi, because square root of pi square equal to pi, and ia, and that's row A. Okay, and yeah. And yeah, so we check that the state we get is actually a purification of row A. And yeah, so this is a purification of our density matrix. We see that any density matrix, you can write all this purification. We have an exact construction. And actually, purification is not unique. There are many of them. And for example, you see that this is also no basis IR here. You can choose arbitrarily. You can choose a different basis for your R system, and you get a different purification, but you will still get the same reduced density matrix. Okay? And yeah, and there are even weirder ways to do purification. No, I think. Yeah. Actually, probably not. But anyway, there are many different states that give you the same purification, same reduced density matrix. So purification is not unique. But usually the most important thing is that there is a purification. So you can think things as just pure state. Okay. And any question about this proof? No. Okay. And yeah, so let's go back to this picture that we had last time, that we showed a little bit last time, and this shows that this is some relationship between Schmidt decomposition and purification. Okay, and so as we said, there are two operations that's kind of the reverse of each other. So it's that you can think about a bipartite system that has an entangled state, pure state. So we have system A and system R, and if we trace all the R part, and then we will get a density matrix on A. So that's a reduced density matrix. Okay, reduced density matrix away. And we also say, and this trace part is actually something you can do kind of physically. You can literally just throw away. Yeah, you can just throw away, or like just seal your system R somewhere. You just don't touch it anymore. Then basically what you get is a reduced density matrix on row A. Okay? But the other part is the purification is mostly mathematical. Okay? So you have a reduced density matrix on system A, and then mathematically you can always find the pure entangled state between pure entangled state on AR such that the traces are equal to row A. But in reality, if you have this OA, but you already throw the system away, then you basically cannot do purification. If you want to do purification, then basically what you need to do is you find all these system and you put them together. Okay? But maybe you throw it away and you cannot find it anymore, then maybe you throw it to the ocean and you drift it somewhere else. And so physically, it's usually impossible to do purification. Okay. Anyway, let's go back to mathematics. And mathematically, then we can see things are described in ways that's kind of similar. We have a typo here, sorry. So this is pi. Okay. And we see that the pure state, that is the entangled pure state, can always be written in the streaming decomposition. That's a summation I square root pi IAIR. And then correspondingly, we have a reduced density matrix that have using the same pi, and there is summation same pi and the same IA, that's summation I pi IA. Okay. So you see that those two forms has a close relationship. Okay, and here we have the streaming coefficient, that's the square root pi. And on this part, and we see that the square of the streaming coefficient are the eigenvalues of rho A, and it's also kind of like the probabilities of different ensemble states of rho A. Okay, and we see that when pi is very concentrated, when the square root pi is very concentrated, so if only one of them is 1 and all others are 0, and then AR will be a product state. Okay. Means it's some pure state on A tensor another pure state on R. And correspondingly, that will mean that pi is 10000 for this rho A, and that also means that this rho A is a pure state. And that makes sense with this because AR is a product state, so you trace all the R part, it doesn't affect the A part, which is still a pure state. Okay, and then if pi is not this closely concentrated, then AR will be an entangled state, and that will mean rho A is a mixed state. Okay, any question? If not, then we go to the actual latest slide of the density matrix. Okay. And this is just something a little more we want to say about this Bloch sphere and the density matrix. Okay, so remember in chapter 1, we talked about this Bloch sphere as a good way to describe one qubit state. And back then we only know pure states, and we say so on this sphere, so on the surface of this ball. Every point corresponds to one pure state of one qubit system. Okay, and sorry. So here you should have a typo again. Point in ball. Okay, and here we have the idea of a mixed state, and you ask does the mixed state correspond to anything on the Bloch sphere? And the answer is actually yes. So remember we say pure state on the surface, and actually the interior of this ball, every point inside corresponds to a mixed state, and it's really nice. Okay, and how you calculate then is also very intuitive. Okay, so that is remember we think every mixed state can be written as an ensemble. As an ensemble mixture, a probability ensemble of a pure state. That means it's a probability mixture of pure state. And so the coordinate of your mixed state inside this ball is just the same mixture of the pure state. So the pure state has coordinate, and you mix them with probability. That's like you averaging over the pure state. And so if you average the coordinate with the same probability, then you will get the corresponding mixed state. Okay, so that's a mouthful, so maybe that's just the example. Okay, so this 000 point is actually the completely mixed state. It's a very special point. Okay, so this is a completely mixed state that one have this is 1 equal to 1/2 identity. Okay, this is 1/2 identity matrix. Okay, and why is that? Because we know the complete mixed state is a probability mixture of 1/2 of this 0 state and 1/2 of this 1 state. Okay, is 1/2 identity. And so if you take a coordinate average of this north pole and the south pole, then you would see that it's at the origin. Okay, so it's the origin with coordinate 0, 0, 0 on this 3-dimensional space correspond to this 1/2 identity. And then we see that it's very nice because you check it out with the other thing. The other thing we know is that this completely mixed state is also a probability mixture of different states. So it's also 1/2 of this plus state and 1/2 of this minus state. And you see that this also checks out because the plus state is located on this plus of x-axis and the minus state is at this -1 on x-axis. And when you average the coordinate of the drawing is a bit funny. Yeah. But so when you average those two axes together, these 2 points together, you also get the origin. Yeah, and yeah. So, yeah. So you see that, and you also see that the complete mixed state is 1/2 the average of a lot of opposing points, and yeah, that's something I think we prove in homework that complete mixed state is yeah averaging of any orthonormal basis state, any pair of orthonormal basis. How do I say this? Is you choose any basis, orthonormal basis inside this 2-dimensional space, and you averaging the 2 basis element, it becomes a completely mixed state, and that corresponding to the origin of this ball is the averaging of all the possible opposing points. Okay. And yeah, so this probability computation of density matrix matches the geometric calculation on the bathysphere, and yeah, it's quite nice. Okay, any question? If not, this will be end of our discussion on density matrix, and we will switch gear totally and let's talk about computer science. And yeah, let's switch gear and talk about computer science. And for now, I think for maybe half to 1 class, we'll talk about computer science just as a small warm-up. Okay. So there's nothing quantum right now. We're just going to talk about classical computation. And okay, and just wondering. So I want to do a small poll. So how many of you here are in computer science department? From computer science department? 1, 2. And then how many of you heard of Turing machine? About 2. And none, so about 3. Interesting. Okay. That's a little annoying, okay? Sorry. Okay. And so people don't have that much background, but anyway, we don't have too much time here, and I want to focus on content, so I guess I will get a very brief introduction of computer science. Okay. So it's just a little introduction about what we think is computation. Okay, so some basic computer science concepts. Okay, because in the end, quantum computation is about a combination of quantum mechanics and computation in the computer science. And we just finished introduction of quantum mechanics, and so now we'll give a very short introduction of computer science. And unfortunately, we don't have too much time, especially because of the typhoon. And so this will be pretty short, and hopefully you can find other resource to to fill up the gaps you have on computer science. Okay. And yeah, so very quick, Turing machine. Hopefully you heard of it, or even if you don't learn it, you heard it somewhere. And so what is a Turing machine is it's basically what the computer theorists think about what a computer is. And so the story is that there are a lot of different ways to do computer. Okay? And you might have your laptop, although you have your laptop and you have a different architecture, you have your phone and etc. And maybe in the old time people use vacuum tube, etc. And there are different architecture, different ways to build a computer. But computer theorists, as a theorist, computer theorists as a theorist, they want an abstract, unified way to define computation. And so this is what I come up with. And this is even before we have an integrated circuit nowadays. So those were this Turing machine convinced sold out by Alan Turing was an abstract way to think about computation. And so we believe that this is a good abstract way to think about computation because all other way to do computation will be equivalent to Turing machine in some way. Okay. And so this is a theoretical machine that look at this. So it's kind of like a real machine we have. So we have a really long tape memory here, and it has a program that dictates what this machine will do. And it has a finite state control here. This is kind of like a CPU machine. It will read the program and decide what it will do now. It has a little bit of memory inside. And there is a read-write head that can read or write on this memory tape. Okay. And so this is a machine with a really long tape, and you will read the program and do things on tape. And so the tape has both inside input and output. So it will start with something, and the program and the finite state control will read the program and get a tape into the corresponding output. Okay. And yeah, so one Turing machine will correspond to one algorithm. So I guess in some sense this is kind of different from the machine we have now, because say my laptop here is pretty general purpose, will do a lot of different things you do, and you can integrate it with real time. But the computation we think in the Turing machine and in this course are a lot easier. Is a fixed text. So each machine or each program will just do one thing. Okay, so each machine do one program or one algorithm. Okay, so one machine will just do one algorithm. That means you give the input and it will put the output. Okay, and this is kind of the computational problem we think. Okay, so an algorithm is something that turns your input to create output. Hopefully most of the time. Okay, so algorithm give you will fix it some input and output, and the input-output relationship is kind of fixed. As opposed to maybe a laptop here, you can change your input all the time, and you will have some corresponding output that you want it to behave. Okay, but anyway, so we're concerned with this quite static static machine. You have one input and one output, and even though it's quite static, it's still pretty hard. Okay, and so the hard part is we want to think about scaling of the problem. Okay. And if one, because the series want to think about how hard the problem is, and how hard the problem is, we'll talk about this later, is how the computational results grow with the system size. Okay, and so the very important feature of the Turing machine here is that the tape is infinitely long. Okay, so tape here we have 3 small dots here, and this means that this tape is theoretically infinitely long. Okay, so you can put infinitely amount of information inside this tape. Okay, so you can have one program that deal with input of both sides. Okay, so that's I think that's the most important part of a Turing machine. That is, the table is infinitely long, and so with just this one program, you can deal with the input of all sides. Okay, and you can also have output of all sides, and yeah. But also something related to this is the program might not end, and that's a different story we'll skip today. Okay. And so that's Turing machine. There's a tape, and you can do computation on it. And series is actually proof that a lot of computation model is equivalent to Turing machine. Okay, and so that's a theoretical model, and let's go to a circuit model. That's a model of computation that's closer to the laptop we have here. Okay. So circuit model is, but we still only run algorithm on circuit model. Okay, so we have a fixed input and a fixed output. Has some fixed input, and we want to see what each input corresponds to the output. Okay, I guess that I should not say fixed input, but anyway, so we want to have the algorithm give you the correct input-output relation. Okay. And but anyway, what's a circuit model? Circuit model is composed of basically two things. Yes, wires and gates. Okay, and the wires will just draw straight lines, and will carry information. And basically each wire is 1 bit. Okay, so usually we'll have one wire is 1 bit. Okay, 1 bit, and that means each wire can carry information that's 0, 1, and our time flows from left to right. So we'll have an input on the left side. So maybe like 0, 1, 0 here. Okay, so wire will carry 0, 1, 1 here. So wire will carry this 1 bit information, and until it hit a gate. Okay. And when the wire hit the gate, it will change the information on wire, and it will do some computational task. And so those are some basic gates you can put on your circuit. So maybe a NOT gate, so it will flip 0 to 1, 1 to 0, and AND gate, and so it's a gate that actually has 2 input and 1 output. So maybe you have A, B inside, and you have A and B as output. That means that it is 1 only if only if both A and B are 1, and you have this OR gate. So A, B inside, and you have A or B as output. That means that if one of A and B is 1, then this output is 1. And yeah, and you also have XOR. That is, if A different than B, then you have 1 here, and A same as B, then you have 0 here. Okay. So you can have all those circuit and gate, and at the end you will get some output string here. So you 0, 1, 0, and you do some gate, then maybe you become 1, 1, 1, something. Okay. So you have input and output, and you see that in classical computation, then wires can become, the wire number can decrease. So basically, maybe you do an AND gate or you do an OR gate, then you have 2 wire become 1 wire. Okay, and but also fan-out is allowed in classical computation because you can copy information. So you can also split 1 wire to 2 wire or even more. Okay, so this is technically this is called fan-out gate. So you think this location here is like a gate that does this fan-out. So you have 0 here, then you split into 2, 0, or you have 1 here split into 2, 1. Okay. So fan-out is allowed in classical computation, but later we'll say it's not allowed in quantum computation because there is no cloning in quantum. Okay, and also we don't allow feedback loop. Okay, so this is a bit tricky because, yeah, because in some system you can actually build physical system with feedback, but here for simplicity we just don't allow feedback loop even in our classical computation. Okay. And so the circuit model, hopefully this is clear enough. So circuit model, what we do is we want to compute some problem. then we will construct a circuit. So we set up those wires, and the left hand side will take the input, and we put the correct gate inside the circuit, and hopefully we want the right side of the wire, you will get the correct, the wire will carry the correct output value. Okay, so that's circuit model. And okay, and in circuit model, I guess this is a different thing. This is actually talking about Boolean function. Okay, so circuit model can compute a lot of things. Okay, so you have the input and you have output. And the most basic thing we want to compute are those Boolean functions. Okay, and Boolean function basically means that you only have one bit output. Okay, so we'll focus. Although not everything we compute in this class is Boolean function, but we think a lot of them are. Okay, and yeah, so this means that this is a function you want to compute, and they only have one bit output. So we can have some n bit input, and they will go to one bit output, so some 0 and 1. Okay? And we justify that we can focus on Boolean function because if you think any function, so if you have a more complicated function, some n bit input to n bit output function, and you can think this is just a collection of n different Boolean functions. So you can say the first bit of output is a Boolean function, the second bit is another Boolean function. So if you want to compute a function of n bit output, you can just compute n different Boolean function. Okay? This might not be a very efficient way to do things, but theoretically you can do this. Okay? And then then we have this concept of universal gate set. That is a gate set that can construct any Boolean function. That means you want to do any Boolean function, so you have some n bit input and 1 bit output. Then you can use things inside this gate set to string together this wires with correct ordering, such that this circuit will give you the correct input output. Okay, something like this. So maybe like that. Okay. So means that a universal gate set means that whatever this input-output relationship you want, you can always construct a circuit from gates inside the set. So and classically we know we know quite a few of universal gate set. For example, you can construct any Boolean function with just AND gate and NOT gate, and even simpler as a universal gate set with just one gate, that's this NAND gate. I guess yeah. There is a few details here, but let's just say universal gate set does this. Okay, and we have 10 minutes. Wait. Yeah, we have 10 minutes, right? We start with 2:10. Yeah. Okay. Then I want to go to this, going to the most important concept now, although we only have 10 minutes left. And so this important concept of asymptotic notation. This is something that you should remember even if you forgot the quantum computation. Okay. And so as we said, this study of this computational complexity is really studying about asymptotic. Is studying about how the resource grow when your problem size grow. Okay, and so before we characterize things, we want some better notation to describe things, describe what we mean by growth. Okay, and so. So we have those asymptotic notation that signifies how things grow. Okay, so as we said, we want to summarize the resource requirement grow with your problem size. So you have the time, space, and gate. Okay, so maybe an example here is that we want to study how the number of gates of your algorithm grows with your input size. Okay. So maybe we want to see we have some specific algorithm that used to add two n-bit number together, and want to see how the algorithm, so in the circuit model, want to see how the number of gates grow with this n. Okay, and say our algorithm has a gate count 24n plus 2 and 2 log n setting plus 16. Okay. And now I think when n go to larger and larger, go to infinity, then the only important thing is then because log n grows slower than n, as calculus told us, then we know that this 24n will dominate all other terms, and we see that in the largest problem size, then the only term matter is this 24n. Okay, so. So we just discover our term, and we think that this this algorithm has this gate complexity 24n. Okay, and will be even I guess lazier. We will even discuss this factor 24, and we think that this is just grow as n. Okay, and to formalize the intuition we have here, then we introduce those big O notation. Okay, big O notation and the big sigma notation and the big theta notation, etc. Okay, so we have those big O notation, this big O notation, and corresponding other notations that tell us how you pick out this n inside this 24n plus 2 log n plus 16. Okay, and so big O notation is like a upper bound of some function. Okay, and so the exact definition is here. We say that some function f of n, we say is upper bounded by some g of n. Then we write it as f of n equal to order of g of n, and this basically means that as n go to infinity, f of n is less or equal to some constant times g of n. Okay, and so if more detail, it means that if n is greater than some threshold value, some constant threshold value n0, then f of n is always less equal to c times g of n, where c is a constant. Okay, and so in this example, we see that this expression is order n. Okay, because as n goes to infinity, this is less than 24n. Although we have other terms, so maybe you want to say 25n. Okay, and so that's big O notation. And then there's a big omega notation that's very similar to big O notation, but just change from upper bound to lower bound. Okay, and yeah, so this is exactly like big O notation, etc. is the lower bound, and we write f of n equal to omega of g of n, means that g of n is the lower bound of f of n. Okay, and yeah, as we said, so just like big O notation, so this means that as n goes to infinity, f of n is greater or equal to cg of n. Okay, and then there is a big theta notation. So we have upper bound and lower bound, and we have big theta notation. BC means base upper bound and the lower bound. So f of n equal to big theta of g of n means that it's both f of n equal to order of g of n and omega of g of n. And that means as n goes to infinity, f of n is within some constant factor, constant factor of g of n. Okay, so there exists some constant c1 and a constant c2, such that the f of n always between c1g and c2g. Okay, and so this thing, okay. And so here are some, I guess, some misuse people will do with big O notation. That's a little annoying. So first thing is people will misuse big theta and big O. Okay, so that's a little annoying. Like when you see this expression here, 24n plus 2 log n plus 16, and so people will say this is order, this is O(n), okay, and that's not wrong, because this expression is actually big O(n). But a lot of time when people say big O(n), they actually mean big theta n, okay, because this is also big theta n, okay. And the difference is big O is only upper bound, but when you say big theta, is both the upper bound and the lower bound, okay. And so that's one thing. And I guess sometimes people will write like f of n like greater or equal to omega of g, okay. And this is I guess this is the idea is correct, but the syntax is just not standard. The standard syntax for this big O notation is you always write the equal sign here. Okay, so even though you know this big O is upper bound, you want to write f of n equal to order g of n. Okay, so this is in spirit correct, but in syntax not correct. Okay. And so also, although you know big omega is a lower bound, you kind of want to write f of n equal to omega over g of n. The correct syntax is f of n equal to omega g of n. Okay, and so those three are the most common sympathetic notation we have: the big O, big omega, and big theta. And but sometimes we will see two other ones. And for completeness and for education, let's talk about it. So there is also a small o and a small omega, and small and small omega is really similar to big O and big omega, except that you have so I should highlight this. You have strictly less and strictly equal here. Okay, so oh, we have a typo here. This should be small. I think, yeah, this should be small. Okay. And yeah, so we say f of n equal to small of g basically means that f of n is smaller than g of n when n goes to infinity. And what do we mean by sympathetic being smaller? Means that whenever constant you pick here, f of n is still smaller than g of n when n goes to infinity. Okay. And similarly, for the big or small omega notation, means that whatever constant you pick here, when n goes to infinity, f of n will be greater than g of n. Okay, and so we have some example here. We have that when n goes to infinity, 2n squared is big O n squared, because this constant doesn't matter. Okay. So when n goes to infinity, n squared is less or equal to n squared. And similarly, this n cubed log n, when n goes to infinity, this is omega n cubed log n, because the constant factor doesn't matter. And yeah, when n goes to infinity, this is the lower bound for n cubed log n. Okay. And then for big omega, small omega, and small, we have those two examples. So we have the n squared, when n goes to infinity is small of n cubed, because whatever constant you pick here, you can, when n go to large enough, you always find n cubed is bigger than n squared. Okay, and also n log n is small omega of n, because when n goes to infinity, just from this log n factor is going to be, this is always going to be larger than this n, no matter what constant you put here. And I guess at least 1 more minute, I want to say a little thing. So I guess for this small and small omega, you might think this is a very hard to use symbol. And indeed, people use them less. And usually, what they use is you want to write a small 1 or small omega 1. Okay. So a lot of time you will write small 1 just as something that's not exactly 0, but goes to 0 when goes to infinity. So maybe you have like 1 over n is small 1, right? It's less than any constant, but when less than any constant when it goes to infinity, but not exactly 0. And also small omega 1 is a little less common, but also C. Okay, so you can also have small omega 1 and maybe like just log n. Okay, so maybe log n or even log n. So it's something you think is kind of small, but yeah. So sorry. So small omega 1 then is something larger than constant, but maybe quite a little, maybe a little small. Maybe it's like a square root log n. So it's like slow is something smaller than log n, is quite small, but it's still more than constant. And I think that's time for today. So next time we'll continue with our asymptotic notation, and yeah, and we'll finish the classical computation, and hopefully we can start quantum computation. But yeah, we are a little late in class because this Thursday is the double cross day, so it's also a holiday, and we'll see you on next Tuesday, and hopefully we'll start on some quantum circuit. Okay, and yeah, so see you next Tuesday.